Assalamu alaikum everyone. We group 5. Our project name is water quality monitoring and automated fish feeder system. My ID is 2006052. Here is our outline. Then abstract. This project creates an automated fish feeding system using an ESP32 microcontroller. It monitors water temperature and pH, displays data on an OLED screen, and allows remote monitoring via a mobile app. The system includes a servo-controlled feeder that dispenses food at scheduled times with power failure recovery to ensure continuous operation. Then introduction. The aquarium industry requires efficient methods to maintain ideal water conditions. Traditional manual methods are time consuming and prone to errors. Our IoT-based system provides real-time monitoring of critical water parameters and automates feeding, ensuring precise and timely care for fish. Each fish species has a specific ideal temperature and pH ranges for optimal health. The system is designed to meet these requirements, providing the right condition for a variety of species like guppies, mollies, and bettas, ensuring a healthy aquatic environment. Then identification of scope. The system offers real-time monitoring, automated feeding, and fail-safe mechanisms for uninterrupted operation. It is also scalable, making it suitable for both small and large aquarium setups. The Blink app allows remote monitoring and data logging, providing a user-friendly experience. Then literature review. Existing systems have focused on either water quality monitoring or feeding. However, our project combines both, addressing the gaps by integrating real-time monitoring, automated feeding, and cloud-based control, offering a comprehensive solution for aquarium management. Then formulation of problem. This project solves the problem of inconsistent water quality and feeding schedules by integrating a temperature sensor, pH sensor, servo-controlled feeder, and an ESP32 microcontroller. Non-volatile memory ensures data retention during power failures, guaranteeing system reliability. Then analysis. The system design ensures accurate calibration of sensor for reliable data, automated food dispensing programmed into the ESP32, power failure recovery through non-volatile memory, a user-friendly interface through the Blink app. Then the following components are used for this project. ESP32 Wi-Fi module, BS18B20 temperature sensor, pH sensor, OLED display, servo motor, register, miscellaneous components for feeding mechanism.
Assalamu alaikum everyone, I'm ID53, and so this is the methodology of our project. So as you can see, there will be a temperature sensor and pH sensor. They will basically send the readings to the ESP32, and it will check with the threshold, and if the readings across the threshold, then there will be notification sent to the user. And also the internal timer of the microcontroller will basically control the mechanical feeder for food dispersion. So this is the step-by-step methods of our project. So firstly, the initialization will take place. So we will set up the feeding interval, the threshold for safe range of temperature and pH, then calibrate the sensors and basically initialize the OLED and servo motors. Then for the data processing part, we will convert the analog signals of the sensors to the output values in for temperature, it will be degree Celsius, and for pH value, it will be 0 to 14 scale. And that we will compare the timer count with the feeding time and show the current temperature and pH values on OLED screen and in the Blink app as well. And for the operation part, we will notify the user if the pH and temperature is out of the safe range or the feeding time has reached or somehow it has been, if the feeding has been somehow disrupted. So we have also integrated a fail-safe system in our project, and the system will basically work on the will access the local time via the Wi-Fi network, and it will be used as a reference for the feeding schedule. So when the module detects the current local time matching with the scheduled feeding time, it will activate the feeding mechanism. And for the feeder, we have used a servo motor to operate the machine. And when the servo motor rotates, the food comes out of the food container to the water. So this is our circuit diagram. As you can see, the ESP32 is connected to the OLED display also with the temperature and pH sensors and the servo motors. So this is the sensors we have used. Firstly, the pH sensor. The pH sensor is calibrated using standard buffer solutions of, as you can see in the pictures, of pH 4, 6.86, and 9.18. And then we have basically plotted a straight line equation through the corresponding voltages we get for these standard buffers, and using that straight line equation we will be able to find any pH in between these standard buffer ranges. For the temperature sensors, we have used a reference thermometer to calibrate it, but as you can see, as we saw that the reference thermometer and temperature sensor gave almost quite the same result, so no further calibration is needed. And the temperature range of the sensor is -55 to 125 degrees Celsius, and accuracy is ±5.5 degree. So it is basically very accurate. And for the mechanical feeder part, we have you basically made some 3D printed components. As you can see from the picture, there will be a screw and some tube for the base, and there will be a holder, and this will be all be connected. And as you can see in the right picture, these all things are connected to make the whole mechanical feeder part. And finally, for the real-time monitoring part, we are use the Blink app for the data transmission and also showing the values of pH and temperatures in the Blink app. And also in the Blink app, we will get the automatic notifications if any of the range is crossed, or or a feeding time is somehow missed. And we have integrated the Wi-Fi connectivity in this data transmission, so it will take continuous power to operate, and it will be always connected to Wi-Fi for any of the information that is needed for the system to work. Thank you.
Hardware design of our project. In the lab, we did not use any water in the tank, so we have used water in the bottle as for monitoring. We have this is the pH sensor and the temperature sensor in our project. And as mentioned before, this is the food container where the food is contained, and this part is the feeder. And this is the pH sensor module. The pH sensor sends an analog signal, and the module makes it analog to digital for the microcontroller to use. This is the ESP32 microcontroller that we are using. And as a power source, we have used an external DC battery. Here is the demonstration video of our project. We have attached this video with our project report. Here are some images of our project. This is the final project, and this is the mechanical feeder, and this is the Blink IoT interface. In this interface, we can see that we are monitoring last 15 minutes of data. In the Blink IoT, we can live monitor the temperature and the pH in our mobile phone, and also we have added a feature where we will have a notification for any missed say, periods or any critical value for the pH and temperature. Here, this is a demo, and also we have added an OLED screen for live monitoring of the water quality. For the novelty of our project, we have mainly integrated two existing market products. So one is a pH meter and temperature sensor, and another one is automatic fish feeder. We have also added the feature of the notification and the live monitoring system. So we have integrated all these three products into one in our project. And we have also added a powerless recovery feature. Normally, what happens on the existing products is that when a power failure occurs in the middle of the feeding time, the feeding time since changes, the system initializes again at the failure point, and the feeding time changes. But for our project, the feeding time will not change. And the failure after the failure, it will recover the previous data. And another feature that we have added, what if the power loss failure occurs at the feeding time, exactly at the feeding time. For normal devices that are existing in the market, when a failure occurs directly at the feeding time, the, uh, the machine will ignore that feeding time, and it will go to the next feeding time and feed the fishes. But for our project, whenever a failure will occur, the system will recognize that failure and notify the owner that a failure has occurred. And as soon as the power comes back, it will feed the fishes as soon as possible. And another feature that we have added is the data recovery. Whenever a power failure happens, the previously saved data in the ESP32 module gets deleted. So the time that we have saved previously is gets deleted. So every time we go into the loop, we store and load the data from a non-volatile memory in the ESP32 microcontroller. In this way, we can we can recover the data whenever a power loss or failure happens in the project. So we have some limitations in our project. The first limitation is its dependency on the Wi-Fi or internet connection, as we are taking our reference time from the NTP server from the local time. So whenever the internet connection is disrupted, the machine cannot work properly, and also the system is optimized for a single missing period, but whenever a multiple missing cycle happens, the system cannot recover. A battery backup can mitigate the power outage issue, but it still does not solve the Wi-Fi dependency. And any disturbance in the sensor can cause improper data to be shown.
Assalamu alaikum. I'm Role 51. This is our design consideration, the aspect, the public health and safety, environmental and cultural and societal aspects that we have considered for designing our project. And this is the impact assessment. That means our project and the subsequent prototype, if we industry produce, what it will affect the society and culture and the health and safety issues, and what we have considered in a legally defined boundary. And this is the sustainability evolution of our project. And look, if the manually fish feeding, there are very problems related to overfeeding, underfeeding, irregular feeding schedules, water pollution, and real-time monitoring. And there is a subsequent increase in hazardous materials or the polluted water that will fatal for the fishes residing inside. If we use a automated system, we can solve these problems. And this is the automated fish feeder cost only. Our project has mainly two parts. What is automated fish feeder part, and another is water monitoring part. This is only automated fish feeder part that is available in market, which is significantly higher than our estimated budget in our project. But our fish feeder cost is considerably lower than that are available in market. And the key features in our design is that the cost of the whole thing is lesser than the existing items available in the market, and the timely food dispersion reduces waste in the water and keeps the fish in check. And the project is also scalable in industrial scale there, so that it can be used in larger cases. And this is our individual contribution. Rose 51 Ahmed Abtahi has focused in mechanical feeder system and the feeder structure and servo mechanism. Mr. Nasmur Shaki, Rule 52, Nasmur Shaki Toshar has integrated the Blinked IoT platform with our project, and she also did the pin assignment, device link, and user interface. And Mr. Maksudur Rahman Turjo calibrated the sensors with buffer solution and thermometer. That means he has integrated the pace sensor, and that has to be calibrated manually at the first. This is the very tough task. And Mr. John to the Plat, the role 54, has implemented the failsafe system, and also he did the circuit diagram and hardware structure making. And we have distributed the various tasks according to skills and preference, and everyone has participated both in hardware and simulation and software part. This is the logbook of present implementation. This is the bill of the materials, which is a total 5,333 taka has been needed to complete our project. And there to calculate the prototype, we have deducted the only project specific cost. The project specific costs are plastic cost, fish feeder, or miscellaneous cost, which are only essential for demonstration. But if we produce them industrially, it is not necessary to include them. So we have deducted it, and to subsequently deducted the cost of the project prototype, the cost of the prototype remaining 4,220 taka. And if we industrial produce, that average bulk discount on components usually 25%, and there is overhead cost of almost 150 taka. So adding that to per unit product cost in manufacturing is 3,315 taka. This is the project management timeline. And in future, we can automatically, in future work, we can automatically calibrate and automatically control the pH and temperature levels. Also, we can automatically control the fish feeding. And also, we would like to implement better fail-safe capabilities that will work under prolonged and shading. And this is the references. Thank you.